sacred institutions. Bedroom eyes, they call them in a bygone day.
Hello, and welcome to Physical Attraction, the show that explains physics, one chat-up line at a time.
But for corrupting others to a life of carnal pleasures and lewd designs. A man whose erotic desires and libertine practices are used to titillate the unsuspecting and would stoop to any depth.
Hello, and welcome to Physical Attraction, the show that explains physics, one chat-up line at a time. Today we're hosting a special episode that's going to focus on the Nobel Prize in Physics 2017. This will replace our usual Saturday episode, because I wanted to get it out there while it's still nice and relevant. As I'm sure many of you know by now, the prize was awarded to three people: Kip Thorne, Rainer Weiss, and Barish. But really, it was awarded to the entire LIGO collaboration. So first I think we'll talk about the prizes in general, and then we'll talk about what LIGO did and why it was important enough to win them the Nobel Prize this year. Alfred Nobel was a Swiss chemist, engineer, inventor and businessman. The whole family had a long history in engineering, and Nobel's father had made his money manufacturing, amongst other things, explosives. Before Nobel, the main explosive that was being used was gunpowder. But gunpowder's actually fairly primitive as an explosive. It had been invented 1,000 years before in China and hadn't really been updated since then. Nobel, in the 19th century, worked on manufacturing new kinds of explosives, including nitroglycerin, which would later become the active ingredient in both dynamite and gelignite, both of which were invented by Nobel. Nobel was not a completely reckless, boomtastic guy. In fact, the whole point of dynamite and gelignite was that they were much safer than raw nitroglycerin, which pretty much explodes at a moment's notice. He even nearly called dynamite Nobel's safety powder, in part to get around several PR disasters where factories producing or storing his substances exploded. But of course, safe explosives aren't safe when they're used intentionally, when they're used to kill people. The invention of dynamite, which was quickly adopted in industry and war due to far greater explosive power and efficiency than gunpowder, well, it made Nobel rich, but it didn't exactly make him popular with everyone. In 1888, Nobel's brother died while visiting France, and a newspaper mistakenly published Alfred Nobel's obituary. By the way, mistaken obituary publishing does happen more frequently than you'd think. I guess people are under a lot of pressure to get the scoop, and not necessarily to verify the death. And in fact, mistakenly publishing people's obituary has, at least in legend, led to at least one death itself. The obituary was not kind to Nobel. Normally, if something's in a foreign language, I would just give the translation. But since it's French, and my pronunciation of French makes French people wince, La marchande de mort est mort. The merchant of death is dead. That was the headline that called him the merchant of death. That's not a nice thing to read about yourself, or a nice thing to consider when you're trying to calculate how you're going to be remembered. The article said that Dr. Nobel, who became rich finding ways to kill more people faster than ever before, died yesterday. It's pretty damning. And this is generally reported as the turning point in Nobel's life, because everyone likes a good story. Did it actually happen? You will find countless sources that repeat the story, but the actual obituary is quite elusive. If anyone listening knows of a copy or the source for this story originally, I'd love to read it. What is perhaps slightly better documented is that Nobel was very engaged in the debate on what his weapons would do during his own lifetime. He had a lifelong friendship with pacifist Bertha von Suttner. Bertha von Suttner was a minor Austrian aristocrat who lived in the 19th century. She briefly worked for Nobel as a secretary and housekeeper, and they became very close friends. So naturally the historical gossip is that he might have been interested, but she went on to marry someone else. Regardless of whatever romantic drama was going on in the background, they remained friends. She worked as a novelist, writing books with an increasingly pacifist tinge to them, and she stayed in touch with Nobel even as she found herself one of the leading figures of the Austrian peace movement after publishing a famous novel, Lay Down Your Arms, that detailed the horrors of war. It's a shame that people didn't listen in the 1890s when she wrote it. The world might have been spared a pretty horrendous 20th century. And as we of course know, they're not listening still. In his letters to Suttner, Nobel expressed contradictory opinions about war and peace and his own role in them. He called war the greatest of all crimes, but he felt uncomfortable acknowledging his own role in helping the weapons manufacturers. So he fell back on a fairly common defence among scientists who manufacture weapons. The more powerful the weapon, the greater the deterrent to armed conflict. "My factories may well put an end to war before your congresses," he wrote to Suttner in 1890. "For in the day that two armies are capable of destroying each other in a second, all civilized nations will surely recoil before a war and dismiss their troops." So, on one level, it's sort of true. I mean, the most powerful weapons we have now have rarely been used, but on another, more pertinent level, this has been shown to be a total crock. And it conveniently allows Nobel to make millions off the manufacture and sale of weapons, while still claiming some kind of moral fibre. It's interesting to note that we still hear some of the same arguments about weapons today, and some similar justifications by scientists who find themselves working in the weapons business. So whether it was seeing the obituary error, or his conscience, possibly embodied by Suttner, Nobel was obviously very concerned about his legacy, and how people would remember him. For this reason, when he died, he devoted 95% of his fortune to setting up the Nobel Prizes in his will. That money has since grown to be worth billions of pounds, dollars, whatever currency you like, ensuring the future of the Nobel Prizes for a very long time, especially if they continue to be only $1 million per prize. Not that I'd say no to $1 million. They've had an interesting history. Nobel's original list of prizes were physics, chemistry, medicine, literature, and peace. Naturally, the Peace Prize probably owes the most to Suttner's influence. Then, later, the Swedish Royal Bank donated a large sum of money to the Nobel Foundation to set up the prize for economics, which may have annoyed physicists who are often highly snooty about what is and isn't considered to be real science. Get over yourselves, guys. This is a total tangent, but I can't resist mentioning it. I recently listened to an episode of the Freakonomics podcast, which is great and you should check it out. The episode was entitled "The Stupidest Thing You Can Do With Your Money," and they were basically having an argument about the following. They said, don't waste your time making investments where the fund is actively managed, as in someone picks shares for you. These active management funds tend to underperform the market when you take the brokerage fees that you have to pay into account. Instead, put all of your money in an index tracker that rises and falls with the market in general. That way, you don't pay fees, and most people who do that end up making more money than the active managers who are betting on the success and failure of individual stocks. I mention this here because I found the people they picked for both sides of this argument pretty hilarious. I don't really know enough about fund management to say for certain whether one method is better than the other, but on the one side of their debate you had a Nobel laureate in economics, and on the other side they had Anthony Scaramucci, the Mooch himself. Somehow they managed to interview him in the 1 week window when he worked at the White House. I found this very funny. Anyway, the Nobel Prizes quickly became some of the most prestigious awards that you could receive, and now they're popularly seen as the holy grail of scientific endeavour. Of course, any scientist worth their salt will tell you that the most important reward is contributing something new to our understanding of the universe and everything in it. But, that's a whole lot easier to say if you also have a Nobel Prize. Marie Curie is the only person to receive Nobel Prizes in both physics and chemistry, and one of a few individuals who managed to get two. The chemistry prize was for isolating radium, and the physics prize was for her work on radioactivity. The rules for awarding the prize have morphed a little over the years. So Nobel's will originally intended that the prize was to be awarded for the work of greatest significance that took place during the last year. But obviously this has a lot of problems. The main one is that it's really very difficult to work out what achievements are going to turn out to be the most significant. In the sciences, for example, some research seems initially exciting, but then turns into a dead end. Some research takes years to be appreciated as important, like Van Gogh's paintings, and some research is invalidated later. So there's a famous example in physics that some of you may remember. In 2011, they thought they'd discovered faster-than-light neutrinos. I was in high school at the time, and I remember asking our high school physics teacher what he thought of it, and he was pretty sceptical. And it turned out he was right. So if this result was accurate, it would have turned a lot of physics upside down. It took until 2012 for people to be conclusively sure that it was a mistake, although most people were pretty confident that it must have been. So what do? Do you give them the Nobel Prize for a research topic that sparked a lot of initial discussion? If you insist on the "in the last year" rule, then you might miss the boat while you're waiting for confirmation. On the other hand, you might give the prize to people who don't really deserve it. There was one particularly embarrassing case in 1926. Johann Fibiger claimed that he had discovered a parasite that could cause cancer in rats and mice, but it was later shown that he'd made experimental errors and this was in fact false. Whoops. So they've relaxed this rather stringent rule, and in fact they've relaxed it an awful lot. Nowadays, it can take decades for people's research to be recognised with a Nobel Prize. So the physicist Chandrasekhar had nearly 50 years to wait before being recognised for his research into stars and black holes. And Peter Higgs, who's credited with the main idea behind the Higgs boson, well, he mostly contributed to the field in the 1960s, but he had to wait until 2013 to win the Nobel Prize as a result. So in some ways, this helps avoid controversies with research that turns out to be overhyped, or even false. For example, as topical at the moment, if they did this delay with the Nobel Peace Prize, we might have had fewer controversial nominations in that particular category. This long waiting period is particularly of concern, though, because there's a rule that you can't nominate someone for a Nobel Prize after they've died. So inevitably, some people's important achievements are going to go unrecognised under this system. Personally, I don't see what's wrong with awarding it posthumously, providing you don't start trying to give one to Newton. How about it's fine for people who've died in the last 20 years or so? But anyway, those are the rules. And of course, they've caused a lot of controversy. Specifically, this year's Physics Prize, which we're now going to talk about, has caused some more controversy as far as the rules go. It was awarded to Kip Thorne, Rainer Weiss, and Barish, but really it was awarded to the entire LIGO collaboration. The prize is celebrating the detection of gravitational waves, but this took the efforts of the entire LIGO team. But there's a rule in the Nobel rulebook that says you can't divide the prize between more than 3 people. So in some ways I can see the argument for this. If you could award it to hundreds, it might dilute the prize and take away from the prestige of the individual effort. And also the cash gift would be meaningless. But that was always secondary to the real nature of what a Nobel Prize is about. The problem is that the way science is done has changed over the years. On the whole, it's become more collaborative. This is a function of how much you know, of course. So it was possible for Newton and even Einstein to just sit and think and deduce new things about the way the universe worked. Einstein was famously working in a patent office for his day job when he came up with some of the insights that would later form the theory of relativity. Newton was holed up in his house while Cambridge was closed due to the plague when he came up with many of his ideas. Similarly, in experimental physics, you have individuals like Coulomb or Faraday who used to be able to set up apparatus in their garden sheds effectively and make groundbreaking discoveries. But now, especially in experimental physics, lots of the work is done by big collaborations. Hundreds of people worked on the LHC in the Atlas collaboration, and many people worked on the LIGO collaboration to detect gravitational waves. And it makes sense, these telescopes are huge. The LIGO detector is 4 kilometers long. The Atlas detector is 27 kilometers in circumference. Both of these experiments would not fit in your garden shed. More and more scientific discovery is being done by huge collaborations of many scientists over many years. So as people have been pointing out for years, it's about time that the Nobel Prize changed to reflect the new story of physics. Not that the people who actually won the prize this year are undeserving. It's just that there are plenty of deserving people who worked with them who, in the history books, won't get an awful lot of credit. The Nobel Prizes also need to answer for the fact that the last 127 physics prize winners have been men. Even though the gender bias in physics is bad, and in academia it gets even worse. So you can imagine that in the nomination process it's probably also terrible. It's still the case that 3% of Nobel Prize nominees over that time were women. So that statistic alone tells you how bad the situation is. Even with that, you'd expect a few of the last 127 winners to be women if it was all equal. Either way, it amounts to a lot of people not getting the recognition they deserve, or the sweet, sweet Nobel cash for that matter. Gender inequality and inequality in general in physics is a huge, huge problem, as it is in education in general, globally. Beyond the unfairness for the individuals who could have had brilliant careers in science, how can we as a species possibly hope to deal with the immense challenges that we're facing, if we only let less than half the population help to solve them? Okay, with all that said, let's talk about this year's prize. It was awarded to these 3 scientists from LIGO for the detection of gravitational waves. Let's talk about what they are, how they found them, and what it means for science. So Einstein's theory of relativity makes two predictions that are important for gravitational waves. First, it explains gravity in terms of space-time being curved. This is a little mind-bending as well as space-bending, but the basic idea is that if space-time is flat, then the shortest distance between 2 points is a straight line. If it's curved, then that shortest distance is a curve. And you can imagine this, just draw a straight line on a piece of paper and then bend it so that it has curvature, and you'll see that it becomes a curve. If the presence of massive objects bends space-time, then we can explain gravitational attraction by saying, objects are still following the shortest distance between points, but this path has changed, and it's now a curve. This explains why we see gravity act on objects in such a way as to bend their paths. Gravity bends space and time, and this causes the path deflections in objects that we see. This theory of gravity is probably not the final word in the argument for reasons we'll get onto in a later episode, but it's helpful to understand gravitational waves, and it has stood up to every experimental or theoretical test that people can think of. So the other thing that Einstein's theory predicts is that nothing can move faster than the speed of light. Not particles, not light itself, not information, nothing. So imagine moving a massive object. We know that this object, because it has mass, because it has gravity, is distorting space and time around it, bending the fabric. The further you get from the object, the less important that curvature change is, but it's there in all of space and all of time. The effects may be minuscule, but the fact is that the space and time around us is distorted by objects that are many light years away. When the object moves, you can imagine that this curvature has to move with it, to reflect the fact that the location has changed. But nothing can possibly travel faster than the speed of light. So, when this curvature moves, when the changing curvature of the universe moves, it has to flow outwards at the speed of light. So this has really profound consequences. Whenever you move, and so your bending of the universe also moves, you're emitting these ripples in space and time, like waves on water, that spread through the universe at the speed of light. Which is one of those ridiculously wild things you can say when you know a little bit of physics. If you're alone, or in public and you don't mind being embarrassed, wave your arms. By the time you finish listening to this sentence, those ripples have travelled a long way. Approximately 1.5 million kilometres, in fact, 4 times further than the moon is. This, in fact, is exactly how the more familiar electromagnetic radiation and electromagnetic waves work as well. So you might remember that we covered it in our episode on radiation, Unusually Hot. Electromagnetic radiation, which includes light, radio, microwaves, etc., it's basically just the universe finding out that electric charges have moved. You move an electric charge, and the information about that motion propagates throughout the universe at the speed of light, in the form of electromagnetic radiation. So it makes sense in a lot of ways. It's actually very analogous, isn't it? You move a mass, which is like a gravitational charge, and the information about the mass moving propagates throughout the universe as a wave at the speed of light. It's just a similar effect for gravity too, which, like the electric and magnetic fields, extend everywhere in space. But gravity is a much, much weaker force than electromagnetism. You might feel like gravity is pretty strong when you're trying to cycle up a hill or climb a mountain. But consider that the entire Earth is pulling down on you, an astonishing amount of mass, and you can still defy it just by jumping up and down. By contrast, electromagnetic forces are much more powerful. This is why we don't need a fancy LIGO detector and years of hard physics to study electromagnetic waves compared to gravitational waves. If you want to study electromagnetism, electromagnetic waves, you can just open your eyes. Gravitational radiation or gravitational waves, they have an amazing consequence too, although really in a more philosophical than practical sense for us. As the Earth orbits the Sun, it's a mass that's moving, and it's emitting gravitational waves which carry away energy. This means that due to this emission, the orbit of the Earth around the Sun is gradually decaying. Given long enough, the Earth would radiate away all of its energy and spiral into the Sun. But this won't happen to us, because the Sun will expand in a few billion years and likely engulf the Earth anyway. So the effect is very small. So since about 1916 and Einstein, we knew that there were probably gravitational waves all around us in the universe. But because gravity is so weak, and the effects of space-time curvature are so small, it was difficult to see how we were going to observe them. But also around this time, we were learning more about the cosmos and some of the insane processes that go on out there in space. What we need to observe gravitational waves is something with a huge gravitational impact. An ant walking down the road on Mars is not going to cut it. We need situations where whole stars are moving and generating these waves. So people thought, well, let's start looking at the most massive and gravitationally dramatic things in the universe. And they thought, what could be more interesting gravitationally than a black hole, an object so dense and so heavy that even light can't escape from it? And they came up with an answer. 2 black holes. It's a rare event that 2 black holes should find themselves close together, but since they're powerful suckers, once they begin to approach each other, things get dramatic. Like any 2 big objects in space, like the Earth and the Sun, the black holes will orbit around each other. Because their masses are much bigger, the gravitational waves they're emitting will be much bigger in magnitude. The closer together they get, the more powerful the gravitational waves are, because the orbit's getting faster and because there's a bigger gravitational effect. As they emit these waves, the orbit loses energy, and this causes the black holes to gradually spiral into each other, and eventually they merge. When they're spiraling in, they spiral in more and more quickly as they get closer and closer together, and more gravitational waves are emitted. Physicists knew that these black holes merging together would be a very good source of gravitational radiation, especially in the time immediately before the merger, when they were still very close together and still spiraling in. After the merger, because the new super-duper big black hole is no longer moving, they don't produce gravitational waves anymore. But how could we detect this on Earth? How can we see the curvature of space and time moving towards us? In the 1960s, people figured out that this might be possible using something called an interferometer. The idea of an interferometer is a little tricky to explain, but it's so useful as an experimental tool in physics. So here we go. Light waves have peaks and troughs. This means that light can reinforce itself, or it can cancel itself out. We call this constructive or destructive interference. That's where it's an interferometer. We're trying to measure when light interferes with itself. So you can imagine 2 light waves as being a little bit like ripples in a pool of water. When a peak meets a peak, they reinforce. But when a peak meets a trough, they cancel out. If you have a pool of water, maybe in your sink or something, and you start splashing and making these nice waves in the water pool, you can see an interference pattern between the 2 waves if they're in different locations. And this is exactly what they were looking for at LIGO. So the detailed experimental apparatus is a bit more complicated, but the basic idea of an interferometer is to exploit this property of light to make measurements of distance. So imagine now for a second that we have 2 light waves that you set off from the same place, so that the peaks and troughs are all aligned. As they wave through space, you have peak, trough, peak, trough, peak, trough in different parts of space. And they're moving too. So you should be imagining a sort of sine wave moving in space. Then one of them follows a path that's ever so slightly longer than the other. Clearly the waves are going to go out of sync with each other. So maybe now, a peak of one wave aligns with a trough of another, because one of them has travelled slightly further, and so it's waved a little bit more. If you then recombine them later on, you might see an interference pattern where the peaks and troughs are cancelling each other out. And then you've demonstrated that the light beams have travelled slightly different paths. And then you can say that the distance has changed. So clearly this kind of instrument is extremely sensitive to changing the distance. In fact, if you change the distance by a fraction of the wavelength of light, you will be able to detect it, because the light pattern you see when you recombine the beams will change. And using a different laser, you could make this distance a few nanometers or even less if you wanted. So it was considered that when gravitational waves come in and they bend space and time, they might change the distance slightly in one direction while keeping it the same in the other. And this difference in distances that we can detect with an interferometer, this is what they're measuring to see the gravitational wave coming through. But we really need to talk about the scale of the challenge that was facing the scientists at LIGO. They have a detector that's 4 kilometers big, and they're looking for changes in the length that are much, much smaller than that. In fact, to find gravitational waves, they needed to build an apparatus that was sensitive to distance to 1 part in 10 to the 22. That means 1 in 10,000 million. If the detector was as big as the distance to the Andromeda galaxy, the distance they're looking for is just a meter. That's how sensitive the device needed to be, which is why finding the gravitational waves was such an amazing achievement by the collaboration. So they built their interferometer, and after a decade of refining it, they finally made the first observation of gravitational waves on the 14th of September 2015, and they announced it in February 2016. It was caused due to 2 black holes spiralling inwards and merging just as they'd predicted. One of them was 36 times heavier than the Sun, and the other was 29 times heavier than the Sun. Such a huge amount of energy is involved that this happened, that very briefly, when it was going on, the black hole merger was emitting energy at a greater rate than all of the stars in the observable universe combined. But since that didn't last very long, the overall energy signature is much smaller than that of stars. So there are so many amazing facts about this observation, I'll just tell you a few of my favourites. First, not only did the waveform, the way the wave looked, exactly match the theoretical prediction for this type of event, but it was actually the first black hole merger we ever knew about. Before then, we didn't even know if it was feasible that 2 black holes could merge together often enough for LIGO to see them. But since then they've seen 2 more, so obviously it's a lot more common than we originally thought. Albert Einstein thought that gravitational waves might never be detected based on how tiny the effect was. The observation of gravitational waves confirms his 100-year-old theory of general relativity once again. This was the last prediction of the theory that we had not confirmed by observation. And the distance change that the apparatus measured was really tiny. It changed the length of the 4-kilometer LIGO detector by less than 1,000th of the width of a proton. For scale, imagine if you can the distance to the nearest star outside the solar system, light years away. This is the equivalent of adding 1 hair's width to that path and being able to detect it. Stunning. What's more, the detection wasn't just a vague, "we saw something, guys." They could actually draw the gravitational wave. It's exactly what you'd expect from the event, and if you look at it, you can see the frequency of the wave increasing as the black holes get closer together and start spinning around each other faster. And you can see what's called the ring down, the point where the black holes actually merge, and gravitational wave emission slows down and stops. So this was a truly dramatic and fantastic observation. We waited decades to come up with a way of observing gravitational waves, and then LIGO spent decades refining their experiment to get it just right, to detect the waves that were this small. Finally, after 100 years of work of one form or another, we have direct experimental proof that these waves exist, and it's opened the door to a whole new kind of astronomy. As they detect more and more events, we'll learn more and more about the most massive objects in the universe. The next big detection LIGO will be hoping to make would probably be 2 neutron stars merging together. This can also happen, and because neutron stars are very dense, they'll probably produce a very big signal too. The ceremony awarding the prizes will be on the 10th of December. The laureates will probably make a speech, but if they're not feeling talkative, there are always other ways to communicate information. They could wave. Thanks for listening to this bonus episode of Physical Attraction. There will be no episode Saturday, but the following Saturday we'll be back with another Teot Wauki special. Time for the housekeeping. We've got another taped interview coming up, this one with my Master's Project Supervisor, so get excited. For those of you who enjoyed our excellent discussion with Phil Torres at Riskology on Twitter, there are 2 pieces of information. The second half of our discussion will be released later on during the Teot Wauki series. It was very relevant to the discussion of AI, so I'll put it out around the time when I do my AI episode in a few weeks. And you should all also know that his new book, Morality, Foresight and Human Flourishing, An Introduction to Existential Risks, is up on Amazon. I've been reading it and it's great so far, so you should all buy a copy, especially if you enjoyed his interview with me. We have a new website, or to be more accurate, we have a new URL. www.physicspodcast.com will take you to our web page. That's www.physicspodcast.com. So when, as I've ordered you to many times, you guys are telling all of your friends about the show, you can simply refer them to a much more memorable address. www.physicspodcast.com. Since we're already overrunning, I'd like to do a few shout-outs to listeners and reviewers as well. Thanks to Jodie over on Facebook and others from the Podcast We Listen To Facebook group for engaging with the show, recommending us to friends, and giving me some advice. Special thanks to everyone who's reviewed us on iTunes. Super duper special thanks to all the Americans, like Unframe of Mind, who said they liked my accent. I can't help that it's so unbearably sexy. I'd also like to shout out to Aussie Ash for calling me a great essayist, which really made my day when I read it. That was just an ego trip, sorry. Thank you guys so much. Writing and hosting this show is a lot of fun, but getting feedback is even better. And the more reviews we get, the more likely it is that we can eventually achieve our goal of taking over the world and educating people about physics. I'm really keen on doing a listener questions episode sometime soon. So if there are any areas of physics you'd like to hear about, questions you'd like to ask that relate to the show, stuff you've heard on the show, my personal life, etc., there are plenty of ways to get in touch. You can email us at physicspod@outlook.com, hit us up on Twitter at physicspod. You can find us via the Facebook page, Physical Attraction on Facebook. And you can leave comments under the shows on our website at www.physicspodcast.com. I read those too, so if you're happy to do that, then that's probably the best way that everyone can do for asking me questions. And there are plenty of ways to have an impact on what we talk about. The more you talk to me, the better idea I get about the kind of things you want to listen to, and the better I can make the show. It's a positive feedback loop. Okay, enough admin at long last. We'll be back next week. Until then, carry on bending space and time.